Hello, y'all. Darrell Lee Weber Jr. back as promised. Slight change of plans will do the last few thermal problems that caused me trouble. So the sound seems okay. You all can let me know if it's the case on your end. And perhaps I can increase the gain just a little bit on the program. Testing, testing. Right? I think that's good. So these last few problems are from the last exam. I'll go ahead and work those out and see if we can work out some details that I missed before. For the first one, and you should go relatively quickly. The first one I have this equation here given. This is the Gibbs free energy. And the first thing we need to do is take this Gibbs free energy and make a thermodynamic identity from it. So one thing to keep in mind is we have to take the derivative of everything in the expression, because any of these things can change. So that would entail the chain rule. All right. And the other thing we need, and is to replace this equation here. So I need to actually make sure that this equation is on my formula sheet clearly. And actually, I do have this one on my formula sheet. So it's this group of equations here. So what I can do is take this one and make it equal to this. So then we go ahead and cancel everything that can be canceled. So I have a minus and a plus PDV. I have a plus and a minus TDS. So now I have Gibbs, the change in Gibbs free energy is negative entropy times the change in temperature plus volume times the change in pressure. And we're doing this because it wants us to get a Maxwell relation in terms of entropy and volume. So you just plug in the thing that doesn't have entropy and volume, you change that up for something else that does have entropy and volume, and then you can Lisa has the derivative of entropy and the derivative of volume to delete the same in the current one, so we can isolate what we need. So we want to isolate this and this. So we choose something with, it'll cancel out the other things. This means we have to swap this in for that. And now we can say negative S equals dg over dt, given that pressure is constant, and V equals dg over dp, given that temperature is constant. So what I'll do is take a partial derivative with respect to the thing on the outside, and that's also going to be, actually let me keep the negative here. Now if I take the derivative with respect to t, I'll also get partial g squared on this side, and that also equals the partial v partial t. So this means that negative partial s over partial t, given that t is stationary and n is the same thing as partial v over partial t, given that e and n are constant. So this is called a Maxwell relation containing entropy and volume. So like I said, pretty fast for that one. The next one is a bit more complicated. So we have three elements: kyanite, andel, andalusite, and sillimanite. And the first thing we're asked to find is which one is stable at the given temperature, which is the normal temperature at the surface of the Earth. So whatever gives free energy is less, is going to be stable if they're all at the same temperature. Looking at this, the kyanite that gives free energy negative 2,444. The andalusite has negative 2,442. And the sillimanite has negative 2,440. So that means that this one is more stable, given that they're all at the same temperature and everything. and the entropy goes like 83, or to say 84, and the entropy here is 93, and the entropy here is 96. And the question asks to calculate the temperature at which one of the other phases should be stable at the same pressure. So change in P equals 0, but the G is changing and T is changing. So we have a graph with G and T. And at the current temperature, which they give us to be 298 K, uh, so I'll do kyanite and selenite this time. So we put the kyanite here, the selenite will be here as far as the plotting of the relative values for G, since we see that -244 for K and -2440 for S at that temperature. And the formula for the scenario is this. And if we were to alter this a bit, we could say negative partial S, these negative S partial T equals partial G. So change in G equals negative S, which is entropy, change in T. So we can say G naught minus, I guess just to say G of T minus G naught, which is G at the default temperature, is negative S change in T. And technically here we're plotting the change in G. So that means since T is on the x-axis, the slope, the m is negative S, and we see that the slope of kyanite is smaller. Should be bigger because it's negative that, but it is going down because it's negative slope. So let me make sure I graph this properly. So that's T naught. This is T new. And it still seems to me that the slope should be going up. So let's think about this momentarily. Oh, that's why I'm looking at G instead of S. So the slope is going to be negative entropy. So M equals for selenite negative 96 entropy, not G. And MK equals negative 84. So this means that the slope of this one goes something like this, and the slope of this one still goes down, but at a slightly less angle. So we can see that here, the two cross. Negative S, negative S. So the new temperature has to be higher for one of these to become more stable, given that everything else stays the same. So we know that the temperature we're looking for is a higher temperature. And we can actually use this equation derived from that formula. All right. So to adjust this a bit, and at the crossing point, the temperature is going to be there and the G is going to be the same. So we can say GK equals GS, which means G naught K minus S change in T. The change in T will be the same for both of them. Which will be this change here. And this is SK equals G naught S minus SS change in T. So change in S minus, let's just say SS minus SK change in T equals GOS minus GOK. And we can say change in T equals G naught S minus G naught K over SS minus SK, right? And those values are from this table here. So it's going to be S minus K, G over S. So let's see what this comes out to. One thing to keep in mind is that these are kilojoules. And I forgot to write the kilojoules. So I think it's 333 when I take the kilojoules into account. Yep. We have 333 Kelvin. So T new equals 298 plus 333, which equals 631K, which is bigger. So it follows what's expected. So given that pressure stays the same, if we raise the temperature to 631 degrees or greater, well, at 631 they'll be equal, but greater than 631 degrees, the selenite becomes stable. And by the way, the andesite became stable at 428. So the fact that the change in G is much bigger means you need a much bigger temperature. All right. So the last one, this won't take long at all. So we have a system, and the multiplicity of the system is this. Those who've been following along, you're familiar with the multiplicity is. And E equals energy is a constant. And we want the Helmholtz free energy, which is going to be this. And E equals 2 E naught. And also it says the system is in thermal equilibrium with the reservoir. So we can actually get the temperature with T equals partial U over partial S in V. And let me see if I can get this to convert properly without having to edit it. Here we go. Just make some capital letters here. All right, so there we go. So we could also say that 1 over T equals partial S partial U in V. So since energy is constant, we can take an integral Actually, I don't see how we can take an integral. Well, energy is constant, but if the energy were to change, it'll give us the temperature since we have the entropy. So S is K ln omega, which is K ln E naught, which is K ln, because that's the energy. So K ln E minus K ln E naught, and U equals the energy. So this is 1 over T equals partial S partial E in V, which equals K over E. So T equals E over K. So now we have T, F, thus equals U is E. We have E minus E over K, K ln E over E naught. So go back to this one. So that means E minus E ln E naught, E over E naught. And we know that E equals 2 E naught. So that's 2 E naught minus 2 E naught. We stay here. 2 E naught minus 2 E naught, 2 E naught over E naught. So that equals 2 E naught minus 2 E naught ln 2. And if I got my ln here, all right. And I believe that is the full answer. So awesome. Kept it short today, just the last few problems I needed to work out. And I can actually feel tiredness with all this studying. So I'll be sure to go to bed early tonight. And remember, I won't have a show tomorrow because I'll be taking an exam. But I'll be back Sunday with some quantum stuff that I was going to do today. And I'll set a time. I'm sure it'll be multiple times throughout the day before I take my quantum exam on Monday. So everybody who watched, if you haven't subscribed already, do so. Make a comment or let me know if you have a question. And remember, I have tutoring available as well as problem solving. So let me know if you're interested. You have a good evening.